So I thought it'd be fun to do some more. Well, so we could just like run Phantom again and do some MHD problems.
Could you turn the light off on your side of the room?
Yeah.
I'll let Ulrich take charge of the lights.
What's the folder called Screw Ups?
Sorry?
What's the folder called Screw Ups?
The folder called Screw Ups. Let's see. Where was that folder? Oh no, that was in the movies. Yeah, it was in movies.
Could you just turn the lights off?
There's a movie called Screw Ups. Yeah, they're mostly just like numerically things going horribly wrong. Like, oh, that's a good one actually. That's actually very relevant to this morning. So that is what happens if you try to form a star and you don't control your div B errors. And the reason this happens is for a good reason we discussed this morning, which is that for numerical stability reasons, we have to subtract the B div B term from the force equation so that if we get strong div B terms, we will not conserve momentum. And so that non-conservation of momentum is called, I'm sitting here nicely in a classroom and suddenly I fly out the window. Yeah. So where you go to nicely form a star, it goes like bang. Yeah, and just explodes out of the plane. So yeah, there you go. How's that for Screw Ups? Yeah, I don't know, just weird things going wrong usually. What else would you like? Something just getting really weird at the boundaries. That was also trying to form a star. I was going to show you the right version of this first. So the working version of this. Well, so for example, actually, I'll get distracted if I go around my laptop too much. But if you want to like change your life, one of the things that changed my life was a postdoc teaching me how to use BibDesk. BibDesk is there on your Mac if you have it, but it's just a thing for managing your .bib file. But it's just a way of storing your papers offline as well. So it really accelerated my life a lot. Oops.
It's like Zotero.
It's just Zotero. Yeah.
It's like Zotero, but Zotero didn't exist back then. And wow, the magic is ADS to BibDesk. So there's a one-line script. Let's, do you want a demo? Yeah, you do now, because I've told you. So let's like say I want a paper by Stone Wandel. Assume you got some good stuff?
Maybe.
Let's take. All right, so towards cosmological simulations, we learned about this one this morning. Just open my terminal, type ADS to BibDesk.
Is it like a pip install ADS to BibDesk?
Pretty much. There's a few things you have to set up with your API key. Basically, it does the magic. Python script happens in the background. Takes like a couple of minutes. If it will go through the paywall, it'll go through the paywall. If it doesn't go through the paywall, it'll get the archive version. And then like da-da-da in my BibDesk. All the links, PDF, blah, blah, blah. It's very, very helpful for like improving your life.
And then you have a collection of like bib files?
So these files all just sit in a folder that gets filed automatically from you, which I never look in. But if you wanted like, so there's a library here, which is like all the PDFs.
You said it was BibTech management? Like,
yeah.
So you can add like a bunch of these entries into.
It does it all for me. Yeah, so I just have one global .bib file that I use for all papers. And then upload that to Overleaf or whatever.
Can you like create subcategories for like the project you're working on?
I mean, that's all like here. So like when I go to a conference, I just like chuck them into a folder for like stuff I learned from that conference. Yeah.
Can you access the PDFs from that list?
Sorry?
Can you like?
Yeah,
okay.
just here. So like, whatever that one is. Yeah. It's magic anyway. Well, so the scrap you've just seen was from this paper here, where it was talking about this divergence cleaning, what we talked about this morning. But there's a blah, 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 test problem, but the last problem is basically that, is like no div B cleaning. And with div B cleaning, you get this nice, beautiful looking jet coming out in the middle. So I was very happy. I convinced myself that MHD and SPH was going good when we could finally produce jets that are a real, definitely magnetically driven phenomena that are real, like not just a B field doing stuff in the background, it's really a magnetically driven phenomena. So, well, I'll just show you the movie version of that, which is...
It would probably be fair to say many PhD students metaphorically died to make that.
Indeed.
To make that work, right?
Indeed.
Before that.
Let's do long version, actually. Big red jet, how about that? So the very simple setup. So it's just a rotating sphere, basically, that collapses under its own gravity, but just with a small amount of net flux. So we were going to run this one. I'm now inspiring you to run this one. I'm going to tell you we're going to run more basic things. It basically just collapses and it's rotating. And then you wind up the magnetic field in the toroidal direction and launch these nice jets, which young stars do. Then you've actually just run out of material. So visualization of this, actually it's a bit tricky how you visualize magnetic fields on particles. This is my best attempt at it, which is, what if you draw like an iron filing on each particle? It's not great visualization because the number of kind of sticks do change with the number of particles. So you'd like a visualization that doesn't depend on resolution. But anyway, here it is, which is quite fun. So you can see the field is like weak and vertical to start with, but basically you wind up this jet into this little tight little, what you call a spring mechanism, or the Lynden-Bell tower, which is this basically tightly coiled column of magnetic field that just pushes this thing. So one thing about jets is they grow. So the Lynden-Bell model of this is called, there's a paper by Donald Lynden-Bell called Why Magnetic Towers something something. And basically the answer is you wind up a toroidal field, one wind per orbit. So the jet goes up at the same rate as the orbit speed that it's launched from. So for example, if you launch from the inner disk, so if you see a jet going at 200 kilometers a second, you know exactly where from the disk that was launched from, if you've seen this model at least, because it goes at the orbital speed from the launching point. Makes sense? So why do black hole jets relativistic? Why are they relativistic? Why do black hole jets go at the speed of light? Well, so they get launched from the disk basically very close to the black hole. So the orbital speed there is basically the speed of light. Hence the jet goes at basically that speed. That's controversial actually in the black hole community because they usually invoke spinning black holes to explain jets. And we would never do that with stars because there's no way that you don't have a spinning black hole. So that's it. All right, let's come to some exercises. So what I want you to do is appreciate some things about MHD from what we discussed this morning. The best way to do that is with some simple examples. So we're on GitHub. This is the same link we had the other day. So Daniel J. Price, CCA_school. And well, first thing, so these are the lecture notes I mentioned. So you might want to click on those and download. So these are the sort of semi-notes from the course I give to our fourth year students. I give a lot more stuff on SPH side of things. This is just the independent of the numerical method kind of notes. But so for example, we derive waves properly here. You can see it's closely following what we did this morning. I can't click, but well, they're all there. You can have a look and you'll see a more detailed version of what we did this morning if you want to have a look on your flight home. So we're in MHD exercises, and we're going to use this little code, which is a code I used for testing a lot of these algorithms. So it is an SPH code, but I don't want you to focus too much on that at the moment because I just want to illustrate. I want you to illustrate for yourselves some of the conceptual things about MHD. So if we can do this together, so basically go on to somewhere that has a compiler. That somewhere could be your laptop, but it could be Rusty if you're not sure about your setup. These are not expensive simulations to run. I'm going to run a 1D simulation first. Okay, so if you're following along. So wget is a text web browser. If you're wondering why my terminal shows fortune cookies, that's a program called Fortune. It gives you a little fortune cookie. You can search for things about magnetic fields if you like. All right, so I'm going to do wget. I'm actually going to go into, let's make a folder. Okay, so with wget, so we can just cut and paste this one from here. All 161 kilobytes of it would fit on the Voyager spacecraft. So one of the things actually I learned really early on, which is a good lesson, is it's really bad to do development in your production code. And the reason for that is so I think it was about 2 months into my PhD, I went, yeah, I've implemented everything. We just need to run it now. And of course, when you implement anything in a code and you try to run it, it's a complete disaster. And so in your production code, the best you can kind of do is implement something that you know should work and debug it till it works. But what's really hard to do in a production code, and I think you've seen that a bunch of times this week, is it's really hard to like actually change the algorithm in a meaningful way or redevelop an algorithm from the ground up. So whenever I've had to do that, it's always been more helpful to start with a ground up code that, and you've seen that. So the way that Phil presented the moving mesh, for example, with just a little bit of Python code. I mean, Python didn't exist back then. But, just developing the concept code of like, does this method work? And then it's not a question about making it fast. It's like, does my conceptual idea have legs or not? And then you translate that into your 3D parallel code. Because the kind of complications associated with a method are very different to the complications associated with running something in like big parallel 3D code. All right, everyone got that? Okay, so you can just leave that somewhere for now, and we'll just make another directory. So we're just going to git clone these examples. Okay, so you should have 2 directories. Oh, sorry, I do need to untar this directory, xvfz. Okay. So you can see it's a simple Fortran code. We could talk a little bit more about writing code if you really wanted to. So one of the things I try to do is structure things, not have everything lying around in one directory. And so I've got a source directory, there's a docs directory which has nothing in it. But we're not going to go in there right now. So we're going to go into the examples directory. And in the examples directory, you should find a whole lot of examples. And we're going to, because we're talking about MHD, we're going to go into the MHD examples directory. Okay, and you will find them all hopefully nicely named. And in particular, we're going to try this 1.75D MHD shock. Why am I doing this one? Because it's a particularly good, interesting case. Okay. Now you need 2 things set. So you need export system equals the name of your compiler. Now, what is this system variable? Let me just explain that. So, okay, so I'm not going in exactly the same direction, but there you go. So in my make file, I just have an if equal system G Fortran. then set a bunch of variables in the make file. And so that's just something I got from some postdoc who was at Exeter who had this system, and it's just sort of propagated through various people who all adopt the same system. So it's just a variable setting that allows you to just turn on a bunch of flags all at the same time. And for example, I've got another one for compilers that no longer exist, like the Sun F95 compiler has a different bunch of flags. So like G4train is not the only compiler that you can use to compile Fortran with. Actually, there's quite a new one at the moment called, so if you work on AMD machines, AMD are actually writing their own compiler called AOCC, the AMD optimized compiler collection, which is built on the low level virtual machine. So compilers come and go, languages forever. All right, so there's two things you need to have set. So you need export system equals G4train. And the way you can check that is you can just echo $system to check what that's set to. Okay, and we need to export the directory of this code is NDSP MHD _ and I'm just going to put that, well, I called mine Flatiron Demo, I think, NDSP MHD. Okay. Yeah, everyone happy with that? That's just where I put it. So the tilde here refers to my home space, in case you hadn't got that already. Nod when you're good. Yep. And if you want to see all your environment variables, you can simply type env. So env will show you everything you've ever set or everything that's been set by your system. So for example, you could do env grep nd, and it will show you, wow, there's kind of thing still, ndsp. Okay, so what's the nd? So my idea with this code, which is a bad idea actually, was that I wanted to run the same, I wanted to run 1D test problems, which are real simple, and then I wanted to just use the same code to run it in 2D and 3D. A bunch of codes do this. In the end, I had to decide at some level, did I want to make this code into a production code? So did I want to strip out all the options that didn't work? Everything I've ever tried is in here. Did I want to continue with that and just make it fast and keep all the options? Or should I just make a 3D code that just has the working bits? And Phantom was the 3D code that just has the working bits. It was a much better idea. Again, so why it's good to split your development from your production, because the production you care about a lot of infrastructure, a lot of parallelization, a lot of how you just deal with the, reading data in and out. 1D codes, we care about different things, just whether the algorithm works. Don't really care if it's fast or slow. Okay, so anyway, in each one of these directories, there is a nice README. You can just read. Okay, so you can have a look in that if you forget anything that we're doing. So there's a couple of hints of parameters you might want to play around with. Some of this is to do with an old article. So, I mean, we're not really going to explore details about the SPH algorithm, so don't worry too much about this at the moment. I actually want you to predict what you're going to see. So that should be basically make. So it's a real good practice to not have any compiler warnings. You can see I'm not following any good practice here. So for example, one of the simple checks I've put in Phantom on the GitHub repository is that to pass a pull request, you must not have any warnings. It takes a while to achieve that, but once you've achieved it in your code, you want to keep achieving it every day. And so it's a simple thing to enforce. You just compile a code with -w error in the GitHub actions. Do you know what GitHub actions are? Yeah. Okay, so GitHub actions are a real useful thing. So let's see. So the probably simplest one is just Splash. So Splash is also a piece of Fortran. So I've got a real simple, so GitHub actions are here. So a GitHub action is basically a file in your, it's in a subdirectory of the code. What do we see? basically, I mean, blah, blah, blah. But in the end, it just compiles the code. And if it fails, it will fail the action. Yeah, so where is this? So if we look in there's a hidden directory called .github workflows. And in that directory, there's just a little YML file called build. And okay, there's a couple of things. I mean, I just followed a template here, but basically it's just types make in the.
Did you make within the shop folder?
Yep. So if that's not working for you, is that not working for you?
I just got a whole bunch of no such file or directory and then it.
Okay, so you need to have this variable set. So this export NDS MHD dir should point to where you downloaded and untarred the code. So in my case, I had this tar file. I typed tar xvfz version 2.1.tar.gz.
Okay, so sure.
Yeah.
Whatever, we're only out here when we're dead. What are they gonna do? They ask
Is everyone good with compiling? Yeah.
I missed the part of the actual. Is that the only thing that's changed?
Say again. Yeah, so let's just go back to, well, so I'm in NDS MHD examples now. I went to MHD /test 1.75D, test 2 1.75D. Yeah. And I typed make.
Thank you. Oh. Okay.
So if I unset system, it should complain to me. So if I try type making now, it should say, well, okay, you don't have system set. So type make system equals. So you can override variables on the command line, but I've told you to do it with export, so you'd only do it once. So export system equals G-Fortran. Yeah, but you can also override it. So you could type make system equals something else, and it would overwrite that. Okay. Does anyone know what a make file is? Do you want a real quick one? I have a good YouTube video. So let's say something very briefly about make files. So if I make a file called makefile, that's it pretty much. And I edit what's in my make file. So make files have one thing in them, which is called a target. So the target might mean hello, and underneath the target, you just type the command that you want to type, like echo hello Phil. Yeah. That's it. Save the make file. If I type make, it tells me echo hello Phil and hello Phil. Okay, so that's first of all, that's dumb, as I don't want to tell me the command that's about to type. Actually, it's helpful if you're compiling code. But the only other thing that's useful in make files is it has dependencies. So when you type make, it always just says the top target in the file. But if I have hello world, so world is a dependency to hello, and right now it doesn't exist. I'm having trouble because my down key doesn't exist either. So world might be, I'm going to put it at, so at is like don't repeat the command to me, just do it. Echo, I'm trying to think of something funny here, but I can't. Wombat. Okay, so what do you think will happen here? So the key thing I've done, so I've got another target called world. So if I type make world, it'll just do that target. Yep, but if I type make hello, which is equivalent to just typing make with nothing because it's the first target, it will do wombat first, followed by hello Phil. Yep, so that's all there is to make files really, is it's just that combination of things just ad nauseum. So why is that useful? It's because then you have things like variables. So what I really want to do is like have a variable, so you'll see things like So if, say I just wanted to print the compiler version number, I'd just do FC, like for example, the flag to G4tran is -V. But instead of putting it there, I should have F flags is like -V. And I put F flags down here. Yeah, and then instead of somewhere in that, it ran G4tran -V and gave me output. Okay. Does everyone understand what a makefile is now? Yeah. So you can see kind of why this is important. So for compiling code, basically you would just have a list of like source files, and the target would execute the relevant compiler command to compile your code. And there's just one generic rule you have to add. So for a piece of Fortran code, if you're trying to develop one, so for example, in these little local makefiles, so I use them just to like little local one that I write, just basically CDs into the other directory, types make in the other directory, and copies the thing back. Yeah, which is just like a helpful way of just typing make in the directory that I'm in. So that's why I have like a write make script that just writes this little file and just does the business in the other direction for me. But in the other directory, let's go back a couple of more steps. So in that directory, I have a makefile, and this one should be pretty simple. So you can see, okay, so I've got a bunch of variables set. But basically, in the end, there's a bunch of, so the first target in this file is one that's officially called crap, which is if you didn't type make 1D, it says, please type make 1D. And the second target is make 1D. So this runs, basically compiles the code with, in this case, it'll be G4tran, some flags, some other flags, -O, create this binary. And this is a list of objects. What's the list of objects? List of objects is my source files with .f90 replaced with .o. How does it know how to create the .o files? Well, that's called a rule. And the rule is defined here. This is how to make a .o from a .f90 file. F90 -C flags, flags. This is a special variable, means the thing on the left-hand side of the equals. This is a special variable that means the other way around, actually. This is the thing on the right-hand side of the colon. This is a special variable, means the thing on the left-hand side of the colon. Yep. So there's no magic in makefiles. It gets complicated because then people write, well, I don't want to write a makefile myself. I want a thing that writes a makefile. So then you get configure and make. So the auto tools, which are the GNU tools, are like tools which write tools, which write tools. So it all gets very like inception in the end. But makefiles are real simple. Okay? Everyone type to make understands what typing make does?
It's an error. It doesn't. No, it's like we understand this. It's just I don't know why it doesn't.
What's your error?
Well, yes. So the path is correct. The path in the local directory and NTSB, but it doesn't see it.
Well, so if you type cd ndsvmhd dir, does it get there? And do you have the code in that directory?
Yeah. It types the path.
Do you have a Fortran compiler installed?
Yeah, I'm on Rusty, so I.
So you might need to module load on Rusty.
GCC.
So module load GCC will get you the GNU compiler collection. Okay, well, from here you can just run it. So it's just run. So there is an input file, which. What's important here? Okay, so we've got a maximum time, a time between snapshots. See, this looks a bit like the Phantom one. I've got a bunch of options. So for example, this is the ratio of smoothing length to particle spacing, what kind of kernel you want. There's some parameters to do with shock capturing. So the extra thing with MHD in SPH is that you need not just a kind of shock viscosity and a shock conductivity, you have to also add dissipation terms to deal with the rotational discontinuities, and that physically that's called resistivity. So you have to have a shock resistivity. In other words, you don't want infinite current sheets in your code, and you have to have something that can dissipate at an infinite current sheet. So current sheet is just when the field flips direction, you have an infinite current in between. And that's a kind of shock. Okay, we want MHD. I've got a million different ways of doing MHD in this code, but we want number 11. And pretty much that's about it. We don't want dust, we don't want self-gravity, we don't want viscosity. Okay, that's it. So should run. So again, you get a series of snapshots. And what should be set up in this directory is some default plotting things. Yes, no? This one? Well, so I can tell what that is because the product of make should have been that this binary arrived in this directory, which is the ./1d SBMHD. Yep.
Did you change anything in the input file?
No.
Then the
I'm just
input file, right? Is the
showing you so you know that it exists. Yeah. Okay, so it runs. I have a series of snapshots. So I want you to think about this before you look at it. So if you splash, well, you can pretty much splash star.dat. Oh, yeah, good point. Okay, so if you want splash, let's do this. Okay, so it will be there on Rusty, but if you're on a Mac, if you're not on a Mac, you just sudo apt get install splash. If you're on Ubuntu.
But we don't have a sudo. We don't have a sudo. It's on Rusty, right? Like I even asked.
If you're on Rusty, it should work from the other day.
Yeah.
Yeah. If you're on your laptop and you're on a Mac, you just want basically brew. Okay, so if you're on a Mac and you haven't got Splash to look at things, you just want brew tap Daniel J. Price all like that. Homebrew like has many hissy fits every time you type anything. Self updates, blah blah blah, new formulae, blah blah blah. Everything's outdated all the time. And then you should just be able to brew, install, splash, and everything should work. Incidentally, if you're packaging your own software, like for just compiling on your laptop, like making your own little homebrew script is like really easy. So all I've done in this one is I have a directory called homebrew, a repository called homebrew all in my GitHub. That's why you typed brew tap Daniel J. Price all. It goes and gets that repository off GitHub. And then the one for compiling Splash is basically you can follow templates, but it's pretty much you specify what packages it depends on, and then basically just what thing you have to type to install it, and everything magically works. So it makes life very easy for other people if you want to like spread your software around. And so I haven't bothered with putting this in the official like homebrew repository. You can just have your own little tap, it's called. And so I actually maintain a bunch of things. So for example, some of these are my colleagues' codes, like MC Fast is my colleague's ready to transfer code. I just made a little port of that because I don't want to install his stupid dependencies like HDF5 and random number generator 2, borrow ++. I just want the package manager to do that for me and everything to work. So that's the advantage of doing homebrews. You don't have to like manually install other crap yourself. Okay, so is everyone happy with, have you got a copy of Splash? Yep.
So it doesn't install the things that it depends on? What is
Yeah, it does.
Oh, it does?
Yeah, yeah.
Does it complicate things or it's just?
Does it what?
You were saying that you don't want to download those things for his version?
I don't want to have to manually compile them myself. I want so most things have been packaged by somebody else.
Okay.
And there will be a homebrew package for it already. So I don't want to have to like manually download HDF5, for example, and compile it myself. I want Homebrew to do that magic for me.
If you already have HDF5, is it gonna download that as
No.
a library thing, or?
No, it'll just keep the one that's there. Yeah. Package management is a way to use libraries. Yeah, and Unix, like Linux, has solved this problem with apt-get and the Mac. There's Mac ports as well, which some people still use, but Homebrew is pretty easy. Okay, so brew install splash, it'll probably tell me I've already got it installed. And apt-get will also work. It'll get you a slightly older version probably, but it'll do for what we're trying to do. Has anyone got Splash version 2? Has anyone apt-get installed Splash? Everyone's on Rusty. Everyone happy? Oh, I'll go through the. Yep. Should still work. Yep. Yep. It's brew tap Daniel J Price, same as my GitHub /all. Yeah.
Did you just call it Splash? So
Oh, that's good.
Anyone having trouble?
No.
No.
No, but it's really like,
It's a strange one.
it's a strange thing.
Or it can fix all of your problems. I'll leave it to that. I'll wait till my brew install finishes so we can be at the same speed. Yeah, should work.
And then have a splash?
No, shouldn't need an HDF5. Oh, you might need to. You might need module load HDF5.
I have exactly the same.
I mean, the homebrew. Oh, if you don't have the homebrew command, you just have to install some like. So just homebrew Mac OS, and there's just a like single command you have to type to install homebrew, which is on Linux you want to use apt-get. So sudo apt-get install. On Rusty, Splash should work. You don't need to do anything. Good. You're fine.
Did you have to modulate HDF5?
I see. You will have to modulate HDF5 because I was mucking around with Harvey in the week.
What was the command to load Yanfei's splash from his directory? Because it's not generally available in the package in the cache.
So I would just go back to this one, getting started on Flatiron cluster. And then there's a section here from the other day, which is Splash on Rusty, which is here, or you can.
You're right. So when I type if you type flash, does it work?
Okay, so I already have it.
We'll see now if we can see it. Yeah, I should like open a Jupyter notebook in preparation.
You won't be able to pop up a window in a Jupyter notebook.
That way we were able to save it.
Oh yeah, you can download the offline files.
But I just download the
Just give me a hands up if you're ready to go. If you think you got Splash, you've run it and everything. Well, you've run the pro, like the 1D code, yeah? Got some outputs. Okay, so I mean, everything we're doing is listed in the README file. So if you want to just plow on, just read through the README. My homebrew is now just reinstalling the universe. So let's just go here. So I want to type splash start at that. I'm gonna like very 1980s text menu like this. Hey, so I've preset for you here a multiplot. So multiplot just plots a bunch of things against X. Yep. So if you could type capital M, you should get a plot like this.
This is actually, if you want to forward next, yeah.
Got one node in the room. Yep. Yes, so if you want to log in, if you want to pop up a window over the network, you have to SSH minus Y. Don't ask me why it's Y, it was X and then it's Y. Sometimes people use SSH minus XY. I just alias my SSH command all the time. Do you know what I mean if I say alias? So if I type which SSH on my Mac, I just have it alias to SSH minus Y so that I don't ever forget to type minus Y when I type SSH. What I mean by an alias is in my in my Mac it's a Z shell RC. There's a bunch of lines that are like alias. There it is, alias SSH equals. Yeah. So I have like alias random word equals.
What's the open? Oh, yes. Oh, you can, oh, in case of the typo.
I have an error. It says error opening floating device.
Say again?
It says
You can use the microphone as well.
I think it's a hex code.
it says error opening floating device.
Are you on Rusty?
Yeah.
So that means you haven't SSH'd with minus Y.
Oh, sorry.
So just for clarification for a few people, so X Windows is the Linux windowing system. So the advantage of X Windows over other things is that it works over remote connections automatically. So one of the things we learned, I mean, this is not advanced visualization, but one of the things you never want to do with visualization is move your data around. You want to leave it where you ran it and you want to visualize in place. So that's why Splash is written the way it is because I want to do the visualization where I ran the simulation and pop up a window over the network. So the only thing that comes over the network is your 500 by 500 pixels, not like your 10 gigabyte data file. Yep.
The apt-get version
Should work.
determine number of columns in the file.
Oh, so you need if you got version 2, you need N splash. And type N splash instead of splash.
Okay.
Yeah, it just means you're on an old version. Yep, beautiful. Okay, so before you look at this, so you will be able to press space in a minute and we'll run through the snapshots. But this is now the physics. Yeah, so what have we set up here? We've set up a jump in basically everything. So let's just take a moment to learn about what we're doing here. So tell me what's going on in this problem. So remember Andrew set up a problem on the board, Andrew McFadden. He had a stream coming from the left, a stream coming from the right. And what was that? So I've got inflow from both sides of my tube. Okay, so there's two shocks was the hydro solution. So this is material is well, so zero velocity here, and I've got, I mean, it's the same thing. You can think of it as a minus half, half. I've got a 1 and a 0. So I've got material coming in from the left at speed 1. Okay, so I have to explain what 1.75 d means. Okay, so how can we have a Vy and a Vz in one dimension? Let's explain this. So we have dvy, dv dt. So let's think about dv x dt. So that would be minus dp dx. Oh, sorry. Any injuries? Okay, that's fine. And then, well, so there's a magnetic pressure as well, which is isotropic. So that's a dp plus half b squared dx, 1 on rho. But there's another term in the MHD equation, so this should have a mu naught in it as well. But in codes, we usually take mu naught equals 1, just like you can take c equals 1 and things like that. Sometimes you take mu naught equals 4 pi, which means that pi equals a quarter. Yeah. Yeah. Legislate that, America. So famously, America tried to still has it legislated on the book somewhere that pi is 3. Yeah, it's true. Yeah, you have that sigh because you know it's possible, right? Well, okay, so what's going on there? So here we have another term, which is a plus d. Now it's a bb. Yep, so that's where we ran into trouble with our, like, this is really a tensor business. So we got a dd what? It was a divergence of bb. So what is that in one dimension? Well, the divergence goes with one of these things. So it means my derivative. So I've got an x that goes with one of these things. And I've got an x that goes with one of these things. So that's my x direction. But if I do this in the y direction, then obviously this term would go away. There's no derivative in the y direction in 1D. I can still have an x direction with a y field. Yeah, so I can still have a transverse velocity, even though in this case, I'm not going to use the Vy to move the particles. It's going to, but it can still evolve according to my Vy if I only have gradients in the x direction. So that's what we mean by 1.75d. I mean, I assume I only take gradients in the x direction, but I can still have a y that's in the b and the velocity field. Why is it uninteresting to do 1D MHD? So nothing that complicated. It's much more basic.
You can't take the curl, right?
Yeah, so you're on the right track.
You won't get the B, you'll just get the E.
What happens to B in one dimension? Someone said constant?
Yeah.
Why do you say it's constant? All right, so div B equals 0. Okay, what is that in one dimension? dbx dx equals 0. Therefore, the only answer in 1D is bx is a constant. Yep, so what I haven't shown in this plot is bx, because it's just a constant. Yep, and should remain so for all time. So in this 1D problem, the div b equals 0 is basically bx should be constant, which it should be in this case. Okay, but tell me what's going to happen now. So I want you to think about this. So this is your shock tube problem, right? This is the hydro shock problem. You got a contact, you got a sound wave, and we're in the two shock case. This was a shock, and a contact. So what are you expecting here? Press play and watch it for yourself. So press space. Or think about your expectations and then compare your expectations to what the solution does. So the red line is the analytic solution in this case. So I'm not particularly interested in the numerical solution at this point in time. I want you to understand what these extra waves do to our discontinuities. What do they do?
Produce multiple discontinuities.
How many?
I'm counting 5.
I think 5, 6. Any advance on 6? How many do you expect?
That's 7.
What are the 7? Fast and slow and alphane and a contact. So I should be able to identify in this. Okay, so remember the shock problem is self-similar. So running it for longer is actually just like running it at higher resolution. It's the same thing actually, because it's x over t. Oh, I'm pressing space. So I mean, whether you care about how good my numerical solution is here, I want you to identify what each of these things is. Okay, so what happens at the fast shock? What's different about the alphane wave? Let's ask it that way. It's jump in the magnetic field, but what is it not? It's no compression. Okay, so compression means a jump in pressure. Where's pressure? Here. So how many compressions do I see? 1, 2, and I see 2 in the other direction as well. Yeah, you can see the contact is here. So what's special about the contact? Contact is also not a compression. It's also pressures flat across the contact. Yeah, okay, so what else do we see? So those must be my fast and slow waves. Yeah, because they're jumps in pressure. Okay, so where's the alphane wave? So what is it? It's a jump in B. Okay, so how many things do I see jumping in B? How many discontinuities? So I see 6. So I go 1, 2, 3, 4, 5, 6. So which one's missing from the BY? The contact, because the contact has got nothing to do with the field jumping. It's just the same thing as the hydro. It's just where the fluids are initially in contact. Yeah. So no B jump at the contact, but I can see fast, alphane, slow. So that identifies this one as the alphane speed, or as the alphanic discontinuity. Let's call it that at the moment. So it's called a rotational discontinuity. It's got no corresponding thing in pressure. Okay, but we've got a jump in BY. And we've got a jump in VY, right? It's a jump in transverse velocity. So it's a shear, basically. Yep, so shear or flow that way. Yeah, it's a transverse wave. Yeah, and so the shock is just the non-linear version of the wave. Yep, okay with that? What else have we spotted here? So we should be able to see, so BZ, more or less a similar story so you can see, well, I'm a bit smoothed out of my numerical solution, but you can see there's analytics, there's 2 shocks here. Yeah, they're not careful calling them shocks. Discontinuities is the general term. So normally we talk about a shock being a compressive thing. So the rotational discontinuities are not compressive. Yeah. So when we talk about current sheets, for example, what do we mean by a current sheet? It's when the field's like changing direction rapidly. Yep, so this is what this looks like here is you think a field is pointing in a certain direction, and then it abruptly changes direction. So that's what a jump in BY means geometrically. Yeah. Is there anything else? I think that's it.
So the slow and alphane waves are really close together.
Yeah, so I guess that's just the way that the speeds have been ordered in this problem. So you can work out what the speeds are. So I want to do a more fancy version of that. So it's easy to identify it all in a 1D problem because they must be nicely ordered. But I want to do a 2D version of this now where we think about it in a bit more detail. All right, so let's do that. And go into, so that's the 1D shock. So let's do a 2D test. So actually I want to show you one just for fun, if we can do this one first. Let's do this one first. It's just real fun. You've all been running Athena all week. Athena is the code we all aspire to be. Yeah, it's the, the standard by which all codes are set. So you need to make clean. So I'm in test 7, 2D current loop. And I type make clean. That's because I'm going to compile in a different number of dimensions. I'm going to compile in 2D. So I can see it says make 2D here.
Did the make clean actually work?
Yep. It just said that one worked, but then the other one didn't work. There's nothing to delete here. I mean, you should really put an -F in your make clean command so that it doesn't care if there's no file to delete. So we're in the test 7 directory. And this is the current loop advection test, otherwise known as the grid code killer. All right. So there's a readme again if you want more details. But 2D this time. And I've got an input file, jadvec.in. You can look at that if you want to. Well, so if you're really feeling brave, you could set the maximum time to be 1,000 instead of 10. So this is 10, we're going to do 10 crossings of the box here. Yeah, so, okay, so if you want to get the benchmark on this, let's look at the benchmark. Gardner and Stone. Jim's not here, so I don't think we're being recorded now. So we're all good. So ultimate scheme, unsplit Gardner of MHD, blah, 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 is like best thing since sliced bread. I mean, this is not being clever, but the number one test here is this current loop advection. So, so T equals 2 is like so this is with the fancy constrained transport algorithm, we get like 2 crossings of the domain. Yeah, and okay, so here if we go a little bit further, so this is the good scheme because it like doesn't square it up after 2 crossings. Yeah.
What is split or unsplit?
So it's about in a grid, you can either do like a 1D problem in Y followed by a 1D problem in Z, in X and Y and Z. So you can just do like 1D Riemann problems. And an unsplit means you don't take X, then Y, then Z. You just do like the 2 or 3D problem. So it's good, basically. Unsplit is good, but it's much more complicated than doing directional split. But why is this hard? It's because of everything you talked about the last couple of weeks. The hardest thing to do across a grid is just moving stuff. So nothing is meant to change in this problem. You're just supposed to be just moving stuff across the grid. Yeah, we're just moving it at a relatively high speed, which makes it a tricky problem. And a lot of the work in the grid-based codes is to just get this problem. Okay, so forget that because I didn't have the option for quantum in the old code, but it's just running some options that don't exist. But then it should, you might want to know what quantum SPH is, but do you really want to know? Okay, here we go. So it turns out you can write Schrodinger's equation. Quantum hydrodynamics is called. You can write down like Schrodinger's equation in a way that looks like the equations of fluid dynamics. The only difference is you have this funky extra force, which is like the del squared of the square root of density or something. So basically, if you want to simulate a Bose-Einstein condensate, it just looks like hydrodynamics with an extra like special force term. So at some point, somebody in my department was interested in doing this, so I was mucking around.
You also do that for cosmological n-body when you're interested in fuzzy dark matter.
Oh yeah, there you go.
Then you rewrite, well, that's the exact same idea.
I mean, I was saying to Vlad, like over dinner conversation, like it's kind of interesting, like people at the school have very broad interests. And that's because like hydrodynamics takes you to a lot of places. You know, there's a lot of places where the same equations crop up with lots of different applications. Okay, so why is my code not running? I must have left some debugging in my code because I've got to press enter a lot. Yours shouldn't need to do that. Yep, should be running. Is it running? You run to test 10? Yep. I just have to press enter a lot of times. Yep, go.
I think I'm being stupid, but I don't have that 2DS.
So just make clean and make.
I don't have in the ND, the file that I unzipped and put on, I don't have the 2D thing, I only have 1D one.
You should be in the examples directory. Is that where you are?
Yeah, I'm in the test thing, but when it's looking for the 2D file inside.
Have you got a make file?
Yeah, I have a make file. I'm saying the file that I unzipped, untarred, doesn't have the 2.
Correct, because you haven't compiled it yet.
Oh.
You don't want to compile it there. You want to compile it in the run directory. I'm going to stop here. So I'm in the examples folder here.
Yeah.
Yeah, in test 7 2D current advection.
Yeah, but I can't make it because I don't have. I get that now.
And the top of this, there should be a make file in this directory, and it just says default 2D at the top.
Yeah, but then it goes into the other folder that I'm looking for a file that is not there. And I looked and.
Were you able to make the one?
Yes.
Maybe you had problems when you typed make. Did it?
Yeah, it
gave you some error?
Make error because it says in the other file that we unzipped, there is not the 2D SP MHD.
So it means it probably probably didn't compile it when it. Yep. So make. Hang on. Probably that your directory is not set again.
I did that. I feel like it's looking in the right place, but that the 2D file is not there.
It shouldn't be there because we should be compiling it.
Oh, I see.
Yeah.
Where have you put the? Is that it?
Yeah.
Yeah.
I'm sure.
Okay, so you want system equals G4.
Oh, okay. I
Yep.
knew I was being stupid. Thank you.
Very good. So same thing again with this example. So you should have a bunch of files, and again, I've set up some defaults for you. Splash star.dat. And actually in this case, well, so if we look at the README, it tells us what kind of plot we want to make. So we want to render column 22. So you can just do minus render 22 on the command line if you want, or minus R22. But what I'm going to do, what is that? That's just a shortcut for going into this thing. So column 22 is JZ. So J is the curl of the magnetic field. So what is this problem? It's really simple problem. The density is uniform, the pressure is uniform, everything's uniform. There's just a loop of magnetic field. So if I plot maybe density and the magnetic field, you should see it like there's just a loop of magnetic field in a box. There you go. And all that's going to happen to this loop is it's going to move that way. So this is kind of a difficult problem because it's like a thing that has got like a loop that can easily reconnect in the middle. So if you have any, which is why it's kind of a good code test as well, because if it's dissipative at all, the other thing that happens is at the edge of this loop, the field just ends and there's no more. And that means there's an infinite jump in B at the edge. So the current is what's the current here? What's the gradient in curl of B? Infinite, yeah. So if I'm looking at JZ, so it's just going to depend on resolution here. But basically you get a loop that looks like that. Yeah, I mean, what have I done here? My box looks slightly different to yours. I was probably trying to do something slightly different. But you should just see, stop, you don't.
You get the magnetic field ones.
Okay, so I'm just doing 2, 1. So Y versus X versus 22. If you want magnetic field, as long as you type 13 at the next prompt, which is the B field, just to plot arrows where the magnetic fields are. Oh, that looks better. And okay, my box looks slightly different size to what I had run before. Yours probably more rectangular box. But the point is nothing changes, and you can run this for as long as you like, and nothing will ever change. So the SPH advantage is these particles literally move. And so the particles just carry this field with them. It's just a tracer, essentially. So if you think of it like this, so the particles literally just move with a constant velocity and carry this field with them. That's it. There's nothing else to the problem for SPH, because advection is the thing you get for free.
Yeah.
Can you just use the microphone? Yep.
So like physically, it's mapping the curl of magnetic field, which is like according to Ampere's law, the mu naught times current density. So how is current density like physically related to MHD problems?
So in MHD, we tend to think of the B field as king. So as in you just have, well, what we derived this morning, we have a dB dt equals stuff. And what nature does is makes a current which makes a magnetic field. And in MHD, we go, meh, we ignore all that. And we're just going to have an equation for the magnetic field. But you're right. It actually in nature goes the other way around. You start with the J first. You move the charges around that generates the magnetic field. But well, why don't we care? Well, we do care. It's in Maxwell's equations, and we are solving Maxwell's equations. We can do it in a kind of, I mean, MHD is just a simple way of getting that all wrapped in. So when we think of J and MHD, we think of it as an outcome, but of course it is the driving thing in the first place. Yeah, but I mean here obviously I have a B field on my particles, and I've just taken the curl of it to plot the current. Yep. Everyone happy with that one? Okay, let's move to the next one.
How do you plot the particles?
So just instead of, so I did Y for column for the, I want to plot Y against X. I said, what do I want to render? I said nothing. And then, well, do you want to plot arrows for one of the vector fields? So if I plot the J, for example, then plot particles says, do you want to plot particles? Yes. Well, that, because it's ambiguous whether you want to plot particles and arrows or just arrows and no particles. Yeah. So the text prompts are not like the best interface in the world. What I was searching for is an interface that, again, works over the network without having to give you a window, just so you can, because its main point of Splash is remote visualization. So I apologize for the clunky interface. There you go. I mean, what's happening? Nothing. J is 0 apparently. Not sure why. Why is J 0? Can't be true. So that's the abs of J. Apparently my sticks are 0. Okay, so I mean, this current would be in principle infinite here, which means if you are not careful with how you switch off your dissipation, you'll dissipate like that like hell. Div B cleaning also affects this a little bit because it's really hard to tell the difference between a current and a div B when it's like infinitely sharp like that. So you do get a little bit of a ripple, but it's basically trivial. We happy with that? Should we move on? All right, so on to this one. So test 5 2D MHD rotor. So again, you can just type make now because you compiled in 2D previously. So as long as you're still in 2D, you don't need to make clean. The only thing I've done differently is change the module that I'm using to set up the initial conditions. So you can see at the top of this little make file, I have a setup variable, which is just set to the name of the Fortran module that I want to swap in. So baked into this directory is like the name of the problem I want to run with. And then it just compiles with that flag set, basically. And if I go into my original makefile, then if you look somewhere in my list of files, there'll just be a $sign. Well, there it is. I guess sources 1D. Sources. Well, okay, so setup, yeah, so there it is, like setup 2D is just added to my list of files that I want to compile. Yeah, so that's the new magic here. Okay, so 2D rotor. Okay, it's a slope limiter. Oh, it's going to want me to press enter. I have to find where I'll put this stupid enter sign. Actually, I think this must be wrong. Yeah, that's what's wrong. So I'm pointing to my development version. I'm going to point to the version that I've just downloaded. I should get exactly the same results as you instead of. So yours should compile in an instant. You can just run it. Okay, if you want to jump ahead, just look in the README. So it's just a 2D version of the shock problem, basically. All that's happening in this one is I've set up a circle. These are all standard MHD test problems, which is why we're running them. So they're the kind of problems that people run when they want to make sure the code works. Then you've seen a few of them. You've seen the Orsag Tang vortex a few times from the Athena. Again, they're not particularly interesting physically, except that lots of people have done them as benchmarks, and they're just good ways of checking your code. But these ones are also a good illustration of physics. Okay, so this is called the MHD rotor. Don't tell me I still have to press enter. So I have to press enter. I still have to press enter. I didn't set it correctly, is that what it said? Oh yeah, good one. Looks better. Well, I can see it's up here. It says going to the right directory now. I'm compiling in that directory. So again, so just like you saw with the makefile, so it's telling you the command it's going to do, and then it does the command. So in this context, it's helpful because it tells you the command it's going to do, and then it does it. So it shows you the line it's using to compile the code. So that's helpful in this case, which is why makefiles do it by default. Okay, good. Let's try again. No pressing enter. So it'll be a little bit slower because there's 60,000 particles. This code is not parallel at all. So it's just running on one core of your laptop. Or in fact, you're probably just running on the Rusty head node all together at once. But there's 60 of you, and there's probably 60 cores on the Rusty head node. So it's fine. So you're in parallel in the class, right? It's called stupid parallelization. Yeah, yeah. Even more embarrassing in parallel. So you don't have to wait till it's finished. But let's just talk about the setup. So all I did there is open another terminal in the same directory. And again, if you look in the README, I've got a minus Y31. Okay, which is just a shortcut for the multiplot again. So multiplot here is big M. Fine. Yep. Okay, you should get a plot like this. And if you want to expand the screen, you just expand your window and you press R to replot, and R again. Okay, so this is the initial conditions. So I'm plotting density, pressure, magnetic pressure, which is half b squared, and the Mach number, which is the square root of v squared divided by the sound speed. What's the sound speed? It's the square root of pressure times gamma divided by density. Okay. Well, so not all of these were in my simulation outputs, so I believe, so I've got this calculate extra quantities set. So I'm calculating these extra quantities from my simulation data here. So I've calculated sound speed as gamma times pressure over density. That's density. V mag is the square root of Vx squared plus Vy squared plus Vz squared. Mach number is V mag over Cs. And this is my magnetic pressure, which is half B squared. Yep. So I've just entered those things manually and saved them, which is just in the examples directory. What you have is this splash.defaults file and splash.limits file. So if you delete those, you get the default splash. But splash.limits is just a file giving you the plot limits. And splash.defaults is like anything you would ever set from the menu is actually just a bunch of parameters in this file, which is a Fortran name list file. Roman was showing some of these with Ramses. It was kind of Fortran's idea of doing parameter files. They're kind of they're kind of fun if you just read them, but if you write them, then they just come out in some random format like this, which is, I don't use these as the parameter. They were kind of the idea of using parameter files. So I wrote my own module to make my parameter files look nice, with like nice comments and things. You should do likewise. It's nice to have nice looking parameter files for your code. This is actually pretty close to a format called TOML. So TOML is Tom's own markup language. So you might be familiar with JSON format. JSON's like the not the Java. Yeah, it's the JavaScript kind of like parameter file format. So TOML is like you've come across like Markdown and like restructured text. They're just like simple text formats that have a defined structure. So there's one called TOML, which is very close to this. You just have variable equal something, which is, if I did it again, I would just make sure it is genuinely TOML format. But it's good to obey some rules anyway. All right, I've got a few files now, Splash. Okay, so tell me what's gonna happen here. And I'm gonna make one more plot actually, which is, how do I want to do this? Actually, so if you want to get rid of the defaults, you can also just change the prefix. So for example, if you're in Splash, you can do a save as. So you save as like SA. You can change the name of the prefix like blob. And it will say blob.defaults and blob.limits. You're going to be like Splash experts. Your supervisors will be horrified. But so then I can just like splash minus p blob to use those files instead of the splash.defaults. So just a useful way of getting back to the defaults if you don't want to overwrite the files is just like give a made up name here, like blah. Yeah. And it will just look for defaults that don't exist and give you back the defaults. Yeah. Otherwise known as the official splash minus p crap option. Ooh, what the heck? Okay, so splash minus p graph will get me back to the defaults. And why I wanted to do that, my keyboard's doing funky stuff now. Hello. Oh, I'm on like, so somehow I've turned on my microphone and it's now just, it's now just repeating everything I'm saying into the terminal and interpreting that as my brother and sister-in-law. How do I turn this off? Escape, I think. Good stuff. Stop it! Please tell me how I turn off dictation. Still going. Stop it.
SSH.
Is anyone in my laptop? Is this ChatGPT gone wild? Think we're good? Think we're good? No one's repeating what I'm saying on the keyboard. Ukulele gone wrong. All right, let's go again. Oh. All right, so we're 2D MHD radar. We got 10 more minutes together. Let's make it work. Well, so I was after with the minus P crap, which went horribly wrong. I just want to plot density and I want to plot magnetic field lines. Okay, let's go Hollywood mode. Okay. So I've got a field that's initially in the X direction and it's fairly strong. And this little blob is just rotating. It's just going to make waves or it's going to make sort of shocks because rotating fast. Oh, and there's a big density jump basically. So that's just like putting a discontinuity. It's like the SOD shock, but a sort of cylindrical version of it. So tell me what's going to happen before you look at it. Make some predictions here. Your science. So Marcus is going like this. That's good for a start. So we're going to get that for sure. Be a little more specific. So what does the magnetic field change about this problem in particular? All right, so let's talk about waves. First of all, how many are there? So same thing as what we did in 1D. So we've got 3 waves. So we're going to have 3 forward propagating shocks. We're going to have 3 reverse shocks as well. So it's going to get complicated. Okay, but let's talk about the directions of propagation. So we've got a preferred direction here, which is the B field. Okay, which way do the alphane waves go? They're going to go that way. Yep. Do they go that way? Which way does the fast wave go? Which way is the fast wave going to go fastest? We didn't really cover this, but there's a cos theta in the dispersion relation. So there's a, come back to our MHD dispersion relation. There's like a omega squared equals k squared over 2, I think. Like sound speed squared plus v alphane speed squared plus or minus. So the plus or minus is fast or slow. And then there's a thing in here, which is basically sound speed squared plus v alphane speed squared minus 4 sound speed squared v alphane speed squared cos theta squared. Okay, so cos theta is the angle between the B field and the wave direction. And the other one we got was omega squared equals v alphane speed squared cos squared theta, k squared. Yeah, so, well, let's put the k squared there. So the alphane speeds, so what we just said intuitively, because we thought about wiggling field lines around, we said alphane waves go that way. So in cos theta, what does that mean? It means that the speed is 0 in the other direction. Yep, so like perpendicular to the field, the speed goes to 0. So the alphane waves go that way. Yep, with a cos theta. So they will go a little bit the other way, but mostly they go that way. And they won't go at all that way. Okay, so which way? So the question, I guess, is where is the fastest speed? Which direction is the fastest speed in? Okay, so the fastest speed is going to be cos theta is 0, which is like the opposite of the way the alphane speeds go. Yeah, which in this case must be the y direction. Yep, and in that case, what's my fastest wave speed? So my fastest wave speed is going to be, it's going to basically give me k squared cs squared. Well, it's going to be that plus that's a squared anyway, so it's a square of that. So I get 2 of them, which cancels the 2 there. and I get sound speed. So the fastest possible thing that could propagate in this problem is the square root of the sound speed plus the alpha speed. And which direction is that going to go in? Up and down. Yep. Okay, now you can play the movie. Yep. And now you should be able to say what's what. And now, and again, so we're looking just, this is just the 2D version of the different quantities that we were plotting in the 1D shock problem. Yeah. Now I'm not changing, why am I not changing file? So I'm just going to go back to my multiplot for a second. Okay. And let's drag it to the size of the screen. Okay. Tell me what you see.
Upper left one for me.
So yeah, Stanley?
Upper left one, because I only just did the.
Yeah, just plotting the density.
Yeah.
Yeah, so tell me what you see even in the upper left one there. I can play with color bars here if you really want. So we can...
Contact discontinuity.
Well, okay, so let's not talk about context just yet. So there's a front, right? There's a front here. So it's asymmetric, and the front here is a lot further ahead than the front here. Why is that? That's the cos theta dependence of the wave speed on the field direction. So the field, we're assuming the field, so the field obviously doesn't exactly stay in the x direction, but in this medium, it's basically in the x direction still. Yeah, so there's a bit of change due to the problem affecting what the field direction is. But basically the fast mode goes fastest in this direction. So you can see this front here is the fast MHD shock. Yeah. So this one is obviously the fast shock, but it's not as fast in that direction because it's trying to go along the B field. Okay, but what else do you see here? Well, I see a bunch of different fronts for a start. Like there's two like very close together here, another one there, another one there, another one there. Yeah, but let's talk about how many compressive things there are. So if we look in pressure, what do we see? So there should essentially be just the fast and the slow. So which way does the slow wave go? Well, it goes the same way as the fast wave. So the directionality is the same. I just got a minus sign here. But the cos theta dependence is exactly the same. So that basically should have the same pattern as the fast wave propagation, but just slower. Yeah, that's all. Yeah, but then you got reverse versions of those, which kind of complicate this a little bit. So the reverse version of those is like, then you got a backwards propagating thing as well from the initial discontinuity. So they go inside this initial sphere, or initial cylinder in this case. Okay, which one's the alpha wave though? There's not going to be a change in pressure particularly, but is going to be a change in magnetic pressure. Yeah. So it's got to be like some of this stuff. Well, it's got to be in between the fast and the slow as well. So we get to put some numbers to it, but I guess the main takeaway I want you to take away is this is just a 2D version of that 1D test. And you can learn to identify what the discontinuities are by the properties of what the shocks should look like. Yep, so when you're flying a spacecraft through the solar system, it's the same game, right? You know what kind of discontinuity it is by, does the magnetic field flip? Or is there a change in pressure? Or is there a, so it's the same kind of game. All right, anything else in here? Let's have a look. Well, so you can go ahead with the Orsag Tang if you like. So you've seen that in other codes. There's a couple of other shocks. So the 1D Brio Wu was, I mean, that attracted some theoretical interest. So you've already done a 3D version of these shock tubes as well. There's a bunch of stuff in here. you've already seen this once or twice already, and Ulrich might show you one again. I don't know. See where you get to. This one attracted some attention because it's a bit weird, the shock solution. So two of the waves like joined together in the Briot-Wu problem, and it's not clear whether that was like physics or numerics. And there's still some argument about whether this is an artifact of doing things in 1.5D or whether it's like really a physical structure. But all codes get the same result. It's just a test problem now. When my code compiles. So mshock1, come on, go again. Oh, stupid code. Okay. Press enter a lot. No, let's not do this. So anyway, you can have a look at that one. I probably have a version lying around. But you see that there's like two little things joined together. In case you're wondering how I plotted the exact solution for the previous shock tube problem, I didn't. So I just used a table that someone put in a paper. So as long as you know the states and the positions of the discontinuities at some time, then you can use the self-similarity of the shock problem, the fact that it goes like x over t, to scale your solution for all time, right? So as long as you know the jumps and the positions at some time, you can make it look like a movie, even though you're not doing anything clever. You're just saying it's a self-similar problem. For the hydro shock problem, I do actually have a Riemann solver that does the actual solution. Okay, so this is the Briot-Wu. Again, ignore the little bumps and wiggles, but this little bump and wiggle is genuine. And this is the weird thing, is this sort of compound shock. So you got like a shock joined to a rarefaction. And that's the thing that people, well, weren't sure about, and there's still some sort of mainly academic argument about it, but it's a bit of a weird thing having these like two things, like it's called a compound wave. Investigate if you really want.
Look in the Ramses MHD code paper.
Right.
They get rid of it by AMR refining in 1D.
Oh, it goes away.
It goes away. Yeah.
Oh, interesting. There you go.
And you can actually get rid of it if you change the. There's a conference proceeding from Axel on work. If you change, you can write the bx and by down as like some kind of sine and cosine. And the compound will always be there apart from when you add pi in the parameterization. They actually showed that this is the mathematically correct solution.
I see. So there's some fun physics here, basically. Even in 1D solutions of the MHD equations, there's some fun physics. So that's all from me. I'm going to catch a plane and leave you with Ulrich to do like. Actually, a really nice example of this week is like, I think Ulrich already mentioned, we sat down and implemented divergence cleaning into Gadget because I complained on day one. So I think it's a really good test of like the stuff we discussed about divergence cleaning this morning, is to like go through some basic tests of that, which you're going to go through together in a real code. If you wanted to run that jet example I showed, that pretty much is just one of the phantom examples that we also have. So same thing we had the other day in this tutorial, which is like running phantom on a shock, for example. So I said like run on a real example. The setup is called jet. So if you wanted to go ahead and run that jet, it should pretty much work out of the box. We thought it'd be more interesting to talk about physics than like just go another like run a black box code. So that's what we tried to do. And then the last piece, of course, is to think about beyond the simple test problems in MHD is what do you do about the divergence constraint in like 3D code in practice? And that's what I'm going to hand over. But it's been great from my personal perspective. I've really enjoyed interacting with you all. And I've been like a student up the back enjoying myself as well, like for half the week. So thanks for having me. And I hope to meet lots of you at like future computational astrophysics conferences and wish you all the best in your careers. So good luck and thanks.
So the first thing we're gonna do is actually we copy again some stuff from my home directory. It should be fine this time because I figured out that the Jupyter Python notebooks are the problem. So you can go to my home directory, which is printed up here, and there's again the Fluid School, and there's now a folder in there that's called MHD. Okay. Sorry?
Oh, I remember last time like needing to go through step.
No, so Ceph is a little bit slow right now, I noticed. It's actually very slow. I needed like 5 minutes to copy this like 100 megabyte folder from Ceph to my home. So we try to do it in your home directories now. I'm not sure what's happening on Ceph, but it doesn't seem to be quite fast.
Running 2,000 jobs.
Well, but it's usually someone being stupid about writing to disk. So it's not like actually running jobs. It's touching disk typically. So you can copy this like anywhere to your home directory, call it whatever you want, and then we go from there. Okay.
What, the whole MHD folder?
The whole MHD folder. Yeah. You just copy this whole folder called MHD to, I don't know.
Yeah, sorry, it's denied permission.
Permission denied. That shouldn't have happened. Oh. So does it say permission denied on one file or?
But mine was just the
Yeah, you don't need that anyway.
No, I saw an iced latte.
So we're here. I don't think we managed to do the notebooks today because we will not have enough time in the end to do the notebooks. But when I'm done today and tomorrow playing 8 hours of Witcher 3, then I will spend my Sunday put that into a GitHub, okay, like everyone else did. Well, if I play Witcher 3 for 8 hours on Saturday, I have to do something on Sunday. Cannot do it.
Is everyone else being denied?
Yeah.
Well,
Just the checkpoint.
you should just being denied on some like notebook stuff.
Okay. All right.
Which you guys don't need because again, we will probably not gonna make everything I wanted to do, but that's okay because you will get some instructions on some GitHub that Jan Fei will share with you after everything's been said and done. Because Daniel was very persistent this week having me work a lot, which is great for me because when I started like doing working on SPH, I got 2 papers, one of which was Daniel's review article from 2012. That was the one that I got, even though my advisor at the time, well, my relations are close to the guys who, put SPH into Gadget, right? Volker Springel and Klaus Stoller. But Daniel wrote a very good review, and I got the Springel and Hernquist 2003 subgrid model to learn star formation, for which they later got awarded the Gruber Prize. Anyway, it doesn't matter. Okay, everyone has a copy of this somewhere now? Then let's actually look, before we do anything else, you guys complained a little bit, so let's go to this MHD folder. It doesn't really matter which one we start with. I want to start with the advect divergence B pulse. And actually, let's go to the Open Gadget Cosmic Ray folder in here. Cosmic Ray is just like, doesn't matter for anything we do now. Just a branch we implemented that into. Okay, so as I said, Daniel and I did some coding, and you guys complained that you didn't see any in-code stuff. So we're gonna look at some in-code stuff. So we go to Gadgets Hydro Loop, which is in here. Okay, so you should see these files. There's a conduction.c, a density.c, a hydra.c, a hydro background.h, kernel.h, and smoothsimple.c. The fun stuff is happening in density.c and hydra.c. The kernel.h is just like defining a bunch of kernel functions. We can actually look at those real quick. So yeah, so you will see a bunch of yeah, you have to make a decision whether your kernel is like 2-dimensional, 3-dimensional, 1-dimensional, and then that's, which one is that? I think that's the cubic spline, maybe. No, Quintic. This is the Quintic spline implemented into Gadget. So this is Phantom's default kernel. We don't use that. We use, for all our simulations, this one. So that's just like these kernel functions that you have analytic expressions for written up in C. Okay, that's all that is. Like, looks a little bit cryptic, but C always looks a little bit cryptic, so no worries. Okay, then the stuff we modified actually is all in hydra.c, so I can show you that real quick. How, and it's actually really true. So there's like from my history, we were always a little bit, it's not a lot of code that we had to modify. And it's never like the writing of code that takes the amount of time, as many of you probably know. It's like the testing and debugging, finding minus signs that should be not there, but you know, that's just how it goes. And there's a switch in here which is called diff b cleaning Trico. That Daniel wanted that I call that switch like that, so we called it Trico. Fine, fair enough. And initially what you do, so it's a bit of a complicated thing. The whole file is 2,810 lines long, but that's the complete hydroforce calculation of Gadget. Okay, so there's a lot of stuff happening there. Not all of this is like super relevant, but how this looks like, you have to define, you have this function, which is hydra data in. That's the local actually. So it's an MPI code. So you have to do this twice because you have to communicate some stuff. So that's the local. So these will appear again in a later stage. So this is grad psi. So that's still on the blackboard behind you. Okay, so there's a equation on the very top that says minus grad psi. So this is the correction to the dB/dt term, okay? So if we search for this term, we will find that at some point we actually update dB/dt with this grad psi term. And that's actually the next thing that's happening. It's exactly what we do. Okay, that's more allocation stuff. Don't go into this now, but this is where actually this happens. Okay, look at the blackboard behind you. There's a dB/dt minus, well, actually that's it. Yeah, there's a minus grad psi. So we remove this term. Okay, and that's all that happens. Now we just need to compute it and evolve it, right? That's the problem. And what Daniel and Terence in their implementation actually evolve, they evolve psi over the cleaning speed. So which is in my code now phi. Okay, so that's a bit convoluted. And I'm not going to do all these numbers, but there's some of these terms that you can actually recover. You can look at that real quick.
if we look at Daniel's and Terrence's paper, they have a nice summary of the equations that you have to implement. Somewhere they do. No, no. Yeah, here. So this is the one that we updated. Okay, everyone follows that. Good. And this is the one we evolve. Okay, and the only thing you have to note is that my phi is psi over ch. Okay, so there's a few correction factors based on that, but what you can see happening in the code is there are three parts. So this is not at all what I want. There's three parts to this. So the first one is one that scales with the cleaning velocity times the divergence itself. Okay. There's this damping term, which is this term. And there's this velocity divergence term at the end, which is this one down here. Okay. And the only thing we now have to do, or you have to do in an SPH code anyway, is, so we're in a loop over I here, okay? So I don't want to waste too much time on this, but we don't have access to like the neighbors in this loop, okay? So we have to go, we have to actually average, do the SPH average somewhere else, and we actually do that down here. Yes, so you can write this. It's all a bit cryptic now. But what you actually did, what's actually written down in these lines here is this part here. Okay, so that's happening down here. Okay, so we implemented this now. So now we want to use. So there's okay. Doesn't matter. It's fine. We checked this a million times. It should be okay. Okay. So we've implemented this now. The task that took me so long was like testing all of this, and that's exactly what we're gonna do now. So we run a bunch of these like advection tests that Daniel mentioned in the morning, and then we look at them with Splash, and then we see the difference. Okay, that's all we're gonna do, and then we see how much time we still have, whether we can like do like a real problem after that. Okay. Okay, so let's go in here, one up in the code directory. There should be a config file in here. And again, because Sketchit is written the way it's written, it's like very complicated. But essentially, what we're gonna run first is we actually run the case first where we do nothing. So this is what Daniel described as Powell 8-wave cleaning, okay? So essentially that's the one we're gonna run now. So you guys should have, if you type module lit, okay, let's do that real quick. We wanna copy all the modules. There's again the script.rusty, one folder up. We copy all these modules out of here so that we 100% don't make any mistake. Load all of these, and then we type make, and then the code should like build. Works for everyone. It's building. It's failing. Anywhere where it failed to build. I mean, mine's still building, so yours probably still builds. So.
What was the name of it? It was a script underscore Rusty.
There's a. Sorry?
We were just supposed to copy the module.
Yeah, we're just like supposed to copy the module block out so we have all dependencies right for compiling the code.
And then what was the command?
sorry.
Yeah.
Make.
Or source that file.
Just type make. Okay. Or if you want to be a little bit quicker, you can always do make clean and make dash. It's a horrible idea because we're all on the head node now. Make dash J20. It's not compiling.
Parentheses somewhere.
Really? Can you copy that whole folder again?
The whole MHD.
The whole MHD folder. Did it compile for you guys? Okay.
Let me try.
Try to copy everything again. That should not have happened. Maybe. Whoops. Okay, almost everyone has an executable now. I'll come back to you, no worries. So we copied that. That's bad, but you shouldn't do that, but we're doing it anyway. So copy this in the simulation directory, which is this one. So you should have something like this now in your simulation directory. Okay. Everyone's still with me? So your simulation, we were in here and we just do a CP of pget should3 and a dot done. Yeah, I work a lot on like very big supercomputers, so I have to secure. It's just like my reflex. Like CP is for you guys exactly the same. Sorry, it doesn't matter for what we are doing. Just one above. So your simulation directory should now be an advec diff b pulse, and it should look something like this if you do an ls minus LTR. So actually, let me do clear again and an ls minus LTR. You get the same error. Did you load all these modules?
Yeah, I put them all at the top of the configured file.
Can you do an ls on the simulation on this directory? Can you do PVD real quick? Where are you? In your home directory? This is really weird. Let me submit with the others real quick and then I come back to you. Okay, what all of you guys are doing now, so you have to, actually we could do that on the head node, but we're not gonna do it. So there's a script in here which you again have to slightly modify because you guys will probably have something like test in here, right? You should probably have something like test instead of preempt. I don't have access to that queue, so I just submit it to this preempt queue, okay? And then we're gonna run the code on 2 MPI ranks. We run it for 2 hours. We don't really need that, doesn't matter. It's done in a minute. And yeah, you might want to change my email address as well because I get a million emails.
Wait, which file is that?
Sorry?
Which file is that?
This is script.sh. So we're in here. Okay, so you should just change Sorry? Yeah, sorry, temp. Yeah, you're right. Not test, sorry. Should be temp. But I am not allowed to submit to temp, okay? So I cannot use that. Okay, and then there's a parameter file that we link the code to down here. We can look into that real quick. It's called pulse advection.par. That's the IC. It's a very low resolution IC, so will look as it will look, okay. And yeah, doesn't matter. The only two relevant parameters for us will be later if we switch on the new diff-B cleaning that Daniel and I implemented, which has these two control parameters, which is diff-B cleaning parabolic sigma, which we will set to 1, okay? Later, not now. For now, we don't do any cleaning. And there's this overclean factor, which is essentially, that's capturing, that's what Daniel explained in the morning. You can you have to make a decision how fast you clean. So there's the CH in this formalism. That's the cleaning speed. And what we do a priori is setting it to sound speed squared plus alpha and velocity squared and the square root of that. That's like not a horrible idea, but so that's the cleaning speed set by your system, but we put in a switch that just can lower the time step by diff-B over clean fac. So we can just be quicker than the system speed in cleaning, okay? But for now, we don't need any of those. And you should be just by doing sbatch script.rusty, you should get something running. Okay, and you can tail that. Did you guys see what I did? Tail -f out.log, and you should get some output. Okay, and now
No, it's also you need to remove the clause.
okay, let's have a look real quick.
Yeah. As in, I just thought that. Yeah, mine's not running. It doesn't submit, it does submit a batch ID and then nothing's running when I check.
That's super weird.
Yeah.
Can I record?
Yeah.
That's still weird. It should not matter for this particular one. It's somehow missing those.
Oh, I copied them into the configure. The config.sh file.
No, that was not the right thing to do. No, it's stuck. Sorry. You just have to copy those on the command line and then type make and remove them from the config. So it will not understand at all what's happening because of the stuff in the config. Okay. But sorry, it's stuck now. I don't know. You said yours is not running?
I think I figured out what it was. I didn't move the executable one as well.
Okay, yeah. So this is my stupid way of doing it. I would not recommend anyone doing it like that, because, well, I mean, you're supposed to put in your job script where the code is and not move the code to where you actually want to simulate. So I adopted a few weird perks over the years. Did that crash? Is that running even? Okay, so my terminal died. Okay. So in your simulation directory, you should then get a new folder if you do an ls -ltr on that, which is called no cleaning. You guys got it? Or I hope most of you got something along these lines by now.
It's not only appear after the job's finished.
After, yeah, it will appear once the job is like, you know, started and started to produce output. But it's not writing any output. Is my job still running, or what's happening here? It's dark. Does anyone have any output?
Yeah.
Okay.
Actually, yeah, the extra timer density.
Do you have like snap? You should get a bunch of stuff that's called snap underscore number.
No, just like output. I'm good.
Okay.
And it's finished. My job is finished.
Can you show me the directory real quick? So you should have.
No, I don't. I didn't use it.
Nobody.
So you can check, yeah.
Okay, something's really weird.
Oh, is it MHD?
The cluster is not. Is the cluster reacting for you guys? Like. Yeah, same for me.
I was afraid you were going to say
Sorry.
Just I missed it, or I forgot. What was the file we supposed to change the parameter?
Did you change anything in config.sh now?
No,
Okay. Okay, let's go copy the modules out of the script.sh, which is one directory up.
Wait. Okay, I think I already did that.
Okay, so you should just be good by typing make.
Yeah, I did that. I'm saying now there was like a parameter file.
Okay. Yeah, there was. So you have to copy this executable one up.
Script recipe.
Yeah, like just like that.
I don't
Sorry. Copy the pgadget executable to the simulation directory, which is one up.
Okay. That one.
Dot. Yeah, done. Go to the simulation and open the script.sh. And change. The only thing you need to change right now is like my email address. And this.
So you showed us some parameters in a file.
Yeah, we didn't have to change anything. It was just this. Okay. Yeah. Okay.
This is a very disappointing email.
Yeah. Well.
Yeah, I know, but
I came today, so I came out of control C in like 7 times.
Yeah, I think the cluster killed itself. Okay. Yeah, mine seems to run now from Seth. Yours is running. Can you do a tail minus F on? Ah, okay.
I think it's because I submitted so long after everything else.
Yeah, but it's running, but it's super slow.
Mine's finished.
Did you get any Did anyone get any snapshots?
0, 0, 0.
That's any other would work. Yeah, we literally just need one after that to make the whole point of this test. Give me a second. You can't. Is yours still running?
Yeah.
Did you get any snapshots past 0, 0, 0?
I haven't checked.
In there's a directory called no cleaning in your simulation directory. There should be something like no cleaning.
Yeah. Let me see. So should we just submit again? I have a snap open.
Yeah, just submit again and we see what happens. So you made it to 001? You made it to which snapshot?
3.
Wow, okay, so it seems to work now.
Now
Yeah. Yeah, resubmit. I don't know what, I mean, the cluster seems to be unstable the last couple of hours, actually since the morning. So, but it's okay. If we kill the cluster, no problem. I mean, you're not a computational astrophysicist before you actually got an email that scared the crap out of you because you actually killed like a big machine because you did something you weren't supposed to do. It's no, like something really stupid. Like I killed one thing I did which annoyed a famous MPA director a lot when I did that, is using the head node of our cluster at MPA, which is fairly big, to do my 3D renderings early in the morning. But he was stuck trying to debug a repo at the time. This was Volker, yeah. And could do nothing because I used all of the head node. And he was like, you're an idiot. You should not do that. I know, but I'm still doing it. Okay, mine is still super slow, but if you guys get in some snapshots, that's fine. Did you guys get in some snapshots?
it's frozen again. My whole thing. Yeah, just like.
Okay, so I kind of expected that this might happen as the cluster was behaving today. So I will just show you what we should see, okay? It's not great, but we can come back to that. So just make sure that you kill all your jobs now so that we don't like really mess the cluster up. If it's not responding, it's not responding. It's fine. Let's see if we can look at this real quick. So let's put this in Splash because that's a nice way of doing it. And you guys, if the snapshots ever come in, you can like try and do that experiment. We just want to plot the density. Oh, that's going to be interesting whether that's doing anything now. Oh yeah, okay. Okay, so what you can see immediately, this is like a really crappy resolution, because if Splash is done plotting it, you can still see the particle structure below. Let's try, actually that's, what's happening here? This is not even the right test. Okay, also nothing's reacting. This is so weird. Let's try it again. So that actually, if you plot the right quantities, it maybe works better. I don't know. Let's see. Okay, cool. That worked. So this is our famous MHD advection pulse test. So we introduced like some perturbation that we actually artificially generate some diff B. Okay, so if the simulation would have worked, we would have gotten something like this. So you see on the left-hand flank, there's positive diff B. On the right-hand flank, there's negative diff B. If you evolve that forward, I think it's doing it. It's just a bit slow. Yeah, you will see it moving a little bit. But it will retain its like diff B, okay? And this is exactly what Daniel said, like this Powell scheme is not very good at getting rid of it. Okay. Okay, yeah, so it's just advected from the lower left to the upper right. But it will never go away. So it will just cross the box a couple of times until we finish the simulation. If we do the same for, actually, let's go directly to the good cleaning case, parabolic cleaning. What we will get then is, come on, this is not even 100,000 particles. So the initial condition looks exactly the same. Let's fix the axis on that actually. And let's go to the next snapshot. Yeah, and you see it starting to disappear. If you go to the next snapshot, come on, do it. This is the implementation that's on the blackboard behind. Okay, we literally put that in that week, and after a couple of, I mean, it will not even make it once through the box. Okay, so it's really effective at like cleaning away diff B. So, yay, we did it, and it's supposed to be much better than before. Let's see about that. Guess I have an answer for that in a couple of weeks. Okay. I'm actually not really sure what to do now, because if the cluster is not working, that's probably gonna be very painful. Yeah.
I have a great idea for what we can do.
Yeah, sure.
What's the best way to get everything off the cluster? Yeah, because we're on account to get shut down.
Ooh.
It's not working. I'm assuming because of the authentication thing.
Yeah, actually, as
I think you want to copy stuff down to your local machine.
so the best.
You just want to download stuff?
Yeah.
Oh, I know the way.
Okay. You're so proud.
You open them up in the Jupyter notebook, right click, download.
Yeah, that's what we tried to do.
Oh, wait. I was so proud.
It doesn't work for like notebooks and stuff, it works for like PNG.
It's a good question, actually.
Does SSCP work?
SCP times out, I assume because it's trying to authenticate, but it never asks for the authentication details. So you can't forward it, so they just-
How do you guys know how much data you need to copy?
Wait, what's the file you're trying to download?
How much data you need to copy?
Wait, what are you trying to download?
And like the tutorials, the notebooks.
And you can't do that with just with right clicking?
No.
Why not?
Because it doesn't have options.
Yeah, it doesn't let you do it with.
You gotta ask
in the terminal.
No.
But you don't have to do it in Ultra. You can just use good old mouse. Yes. That's why. Why would you want to do it? You can just tar it and then you're downloading one thing, right?
Okay, well, it didn't work.
I tried that yesterday and it did not work.
Okay. I mean, they don't like if you do SCP for some reason.
Yeah, it was just telling me that like it didn't exist, and I was like, they didn't already take my account.
So this works for me, and I've been able to copy all of the directories in my liking.
Wait,
And everyone else tried that, but it didn't work for everyone else?
I tried that and it was like, we can't find it.
Okay.
Let me try it again. It was literally the last thing that I ran.
Yeah.
It tells me. Maybe don't use like the
Yeah.
home.
Don't use the home.
Yeah.
Like use the full. I tried using the full path name. It also didn't work.
Can I see my? Yeah, but you're copying. Like you're copying the signs. I think here.
Yeah, I could try the whole.
Yeah.
I mean, I hadn't tried the whole thing yet. I figured I'd.
Yeah,
just
try
trying
the
to do
full
things small and
directory.
Yeah, I think the full directory is definitely a better idea.
Like my full home directory.
What did we mess up?
Yeah, no, but you ended with.
Every single file and download what happens. So people are running MPI jobs are running Gadget on the Skylake node without module load open MPI OPA. This is on the OPA fabric.
Oh, and that generates it.
For some reason, it's crashing the nodes, which is not supposed to do. But
So it's not our fault, but kind of our fault.
Yeah, exactly. Yeah, so you just tell them to load.
What do I need to load? That was probably my fault because I usually run on the long nodes.
No, because the nodes for the summer school are Skylake nodes. So it's fine. You just need to load the OpenMPI-OPA module in addition to the OpenMPI module.
So I need, in addition to this, I need module load.
Okay,
This one?
Yeah. Just do SS. Did you set up? It just sets an environment variable that tells MPI to use the OmniPath network OPA.
I remember that this is on the Skylake.
Just as
Okay.
Yeah, we might have to recover some nodes.
Okay, sorry about that.
Yeah, no problem.
Okay, so what happened to me now is exactly what I described to you. Someone came yelling at me that I'm doing something stupid. Thanks, Lima. I tell you what we did wrong in a minute. Apparently, I forgot. I'm never running on the nodes that you are running. So in addition to all the modules we loaded, we need to load. We need to load OpenMPI minus OPA. Okay, so this is the module we need. I don't quite understand why everything worked last week still, because we didn't do that last week. But this has to do with the architecture of the Intel Skylake nodes that you guys have access to, but I usually don't use those. So if we load this module and we put, so listen to me carefully, okay? So we actually killed a lot of nodes right now. So we need to load this module, okay? And we need to put it in our submission script. So we need an additional line in our script _rusty.sh that says module load openMPI minus OPA. Everyone got that? Okay. That has to do with the architecture of the Skylake nodes, which again I never use those. So. Sorry? No, you still need the other OpenMPI. You still need the regular OpenMPI. You just need this additional line in your job script, and we need to recompile the code. Okay. You need this. Yeah. Okay. Let me be very, very clear. Okay. Let's do it together. Okay. So let's go to the code directory. Okay. Let's do a make clean. And then let's do a clear, and I do a clear. And let's type module list, okay? And if you type module list in your terminal, you should have something like this. So there should be an OpenMPI 4.0.7 and an OpenMPI minus OPA 4.0.7, okay? Is this what your module list looks like at the moment? Sure. Okay. In that. Well, actually, the code would probably compile without it, because we're not running anything where anything of that is involved. But it should look like this now. So then you can type make, and then we can try to resubmit this test case and maybe not kill any nodes. Great. You got the full computational astrophysicist experience. Killing the cluster at your last day. Love it. Okay. Actually, I'm in the wrong directory now. Yeah, I'm not sure if this cluster will recover before we're done. Yeah, mine as well. So. I guess we call it a whoopsie daisy and. Okay. Yeah. Great. Well, yeah, it is an important experience. Lehman's quite nice. There are people who are not as nice as Lehman. Okay, maybe we can come back to Julia. For you, the SCP minus P worked. Is that something that folks have tried yet, like SCP minus P, and that works for all of you? With capital P, yeah, capital P. That should work. Okay. Other than that, let me actually see whether my notebook's working. It's It's actually still okay if it's just that, but it made the plots. So I would have liked to actually run this shock tube test with you guys to then show you how this cleaning scheme like works on something which is maybe a little bit more physicsy than just like advection of a divergence error. So as we cannot do that now, we will just look at it, and I will very briefly. So this is the same shock tube than Daniel actually, the same one than Daniel ran. So what you see for this, so where's this thing coming from? You guys remember from a couple of minutes ago? That's the compound wave. And people are not sure whether that's like physical or like numerical. Some folks still write papers about this. I even tried to like, when I, handed in my PhD thesis and I knew I had a job, I spent like a month working on this, but figured out that it's actually already in the Ramses code paper. So the trick for the guys in Ramses was like to just AMR refine this like crazy, and then at some level it went away. But it's not clear whether that's like due to numerical diffusion or we don't know, right? So there's still people working on it. So the shock works, looks fine. The interesting panel here is the diff B. So this was when we applied no, Powell diffusion, essentially, Powell cleaning, essentially. Then you get like a divergence error of like 0.02 at this, this is the contact discontinuity, right? Yes, no, yeah, I think so. Anyway, there should be none, right? But we have it. So let's make it worse. So this was the first test we did then once we had it in. That's where we actually switched the parabolic term off. So the interesting thing about this is, so this is without a dampening term. And as Daniel explained in the morning, this is kind of a wave function, okay? And that's kind of neat because what you see post-shock is there's a lot of these like oscillations, right? So this is just undamped waves that move this way. You see also some of them pre-shock. Anyway, so you make it worse by doing that. So if you only do half of it, you actually make things much worse. So you actually need this damping term to get a numerically stable scheme. So these things are always signs of like being numerically unstable. Okay, so we made it worse first. Okay, let's add the other term. And when we do that, we see that we're an order of magnitude better. Okay, so we just improved our method by like an order of magnitude, and we get rid of all these ripples back here. Okay, so that is the idea of this method, and you can quantify that by actually looking at the mean of diff B. And if you look at the mean of diff B, you do nothing. Actually, I'm still pretty happy with it. The code's like not doing horrible. If you take the mean of it, we're somewhere around 10 to the minus 5. That's because there's a lot of scatter, and you take the mean of a quantity that has a plus and minus sign, right? So you end up with a very small number. That's actually good as well, because it actually tells you that your error is symmetric, which is, if you can not do anything better, then at least your error is symmetric, okay? But we can do better now, and it's roughly an order of magnitude better, right? And it still goes down at the end of simulation time. So this is the good thing. And yeah, that's where we are with this. If you look at the MHD pulse, is more striking in that case, because you really see that you do something horribly wrong when you don't put in the parabolic part of it. So without a damping term again, but the constraint cleaning seems to like just work perfectly. And again, you see perfectly fine that this pulse is like preserved forever, right? So there's no change in divergence. I'm actually not sure why it's increasing. So that's something I haven't figured out yet, why there's this slight increase. I guess it's from the particle. It's a very low resolution test, so I guess there's some redistribution noise within the kernel or something like that. Yeah, but that's essentially what Daniel and I did this week. That's why you didn't see me around a lot, because I tried to do my job in the morning, and then Daniel came to my office in the afternoon and said, "Oh, we need to code." Yeah, anyway, I think all in all, we crashed the cluster. That's pretty good. Maybe a good time to call it a day. I hope you guys had fun here. Apply for postdocs here. It's a really great place to be. You get a massive computer, not a lot of people on it.
Are you still a postdoc?
I am, yeah. Yeah. Why?
No, I just thought you had I thought you were a permanent position here. I didn't know.
No, that's why I'm a postdoc. That's why they made me give the most tutorials and the most lectures. I cannot complain, right? Just kidding. Yeah, I'm still a postdoc. Yeah.
What are the other options? Like, can you tell us about what are the other positions of people that are here?
Here?
It's like not
I mean, it's a little bit. It's a little bit different than the classic academic hierarchy. So above me, like, it's not really above, right? But well, it is above. There are the so-called associate research scientists, like Jan Fay, for instance, is I think he's an associated research scientist. Above that, there are the research scientists, then the group leaders, and then the director. That's the hierarchy in a nutshell.
what are permanent positions?
And everything above me. I think they're pseudo-permanent in the sense of like their contracts have like no, I don't know how it works. Haven't seen one of these yet.
To be a research scientist, you probably need to have done a postdoc.
Yeah, so it's the idea for the ARS, for instance, is that it's kind of assistant professor level, and the idea, at least that's what I get from it, so other people might interpret this differently, was that some of the ARSs will eventually get on like associate professor positions somewhere, so that the pool of ARSs can be filled up again from people externally. But there's then also the possibility of here to become a research scientist. And yeah, the problem here a bit is if you're a research scientist, at least my understanding of this is it's not very straightforward to get to work with students. That's why we have the pre-doc program to get young blood in, I guess. And yeah, it's working fine. I mean, again, it's a great place. We have a lot of freedom. There's a lot of funding for stuff like you guys were part of, like the last 2 weeks. That's typically other places would have struggled to accommodate as many people for 2 weeks. So it's really a great place to be. So just send your applications here. Okay.
Are you trying to stay here or go elsewhere?
Why is this about me suddenly? I mean, well, we're trying, right? It's not always straightforward. I think some people like to keep me around for a bit longer.
Just curious.
I mean, yeah, I'm writing something with Greg, so he can do something about it. Yeah, you guys have any other questions that you wanna have answered? If not, I hope you guys had fun the last 2 weeks. I hope you learned something as well. I hope you enjoyed the city. It's like not the worst city to be in for 2 weeks. Yeah, and then I hope that you all get home safe again. And I hope to see some of your faces again next coming months and years. Okay, thanks guys.